In part 7 of the Introduction to Standardized Echography, we will discuss the role of small acoustic interfaces, scattering at these interfaces, and most important, tissue differential diagnosis. At first it was a question which frequency to use for the standardized scan in the differentiation of tissues. The choice of the best frequency was obtained with the help of a tissue model, side-treated blood, with a cell count of 3.6 million cells per cubic millimeter. We see here the echograms obtained from this tissue model with 1 up to 15 megahertz. At 1 megahertz we don't get any signals from the tissue model. This is the initial spike. At 2 megahertz a few, then more at 4 and 6, and the highest signals were obtained with 8 megahertz with a fairly small and acceptable decline in spike height from left to right because of absorption, a small angle kappa. With 15 megahertz, this absorption was so strong, the angle kappa so big, that it was decided not to use that frequency for the tissue differentiation. We also evaluated the tissue model with a cell count of 1.8 million, and you can see that neither at 1 megahertz nor up to 6 megahertz we could obtain any signals from this less dense side-treated blood. Only at 8 and 50 megahertz we got noticeable signals. Again, here at 50 megahertz the sound absorption was too great, so we decided to stick with 8 megahertz as the main frequency in standardized scan for the differentiation of ocular and orbital tissues. And now the discussion of small interfaces, acoustic interfaces. They are smaller than 0.5 millimeters. They cause scattering. And remember, the small size is not more than 3 times the wavelength when we use 8 megahertz. And when we examine a small interface with the 8 megahertz sound beam, then the interface scatters ultrasound into all directions very weakly, so the echo that would come back is very, very weak. Maximal echo is obtained when the interface is centered in the beam. There is no need to be perpendicular to anything. The beam direction is irrelevant. Since most abnormal ocular tissues consist of myriads of small acoustic interfaces, scattering is the basis for their acoustic differentiation. It should also be understood that the sound beam reaches a huge number of small interfaces simultaneously, so that a weak but recognizable echo signal is obtained. And we did several experiments to clarify where tissue echoes come from. And citrated blood played the key role in investigating the echo origin in tissues and understanding the acoustic differences. This again is the series of echograms obtained from citrated blood samples of different cell density from 10,000 to 11 million cells per cubic millimeter. And we see that the reflectivity caused by scattering in this case increases to 3 million plus and then decreases again at higher cell concentrations. The first experiment was done with normal citrated blood, 3.6 million cells per cubic millimeter. That was at that time our tissue model. And this is the echogram obtained from this tissue model before centrifugation. Then we centrifuged and examined again, and you see no signals from the plasma, no signals from the cells. And then after the stirring, we waited for 5 minutes and the echogram was building up again as a sign that we had not destroyed it, the sources of the echoes, by the centrifugation. When you look carefully, you see that this signal between plasma and cells actually has two peaks, and we will see this in a moment with the next experiment. But the important echo sources in tissues are obviously interfaces between cells and intercellular substance. That's the result of the first experiment. In the second experiment, we used citrated blood, same cell count, from a patient with acute leukemia. Here, the echogram before centrifugation, and then here after centrifugation. These two little signals are artifacts from the wall of the glass container, but basically there are no signals from the plasma again, no signals from the red cell count, but we have here a third compartment, the white blood cells. And there's strong signals at the border of each of these compartments. Now these are the two peaks that we have seen in the previous experiment, being very close together, now separated by the large amount of leukemia cells. After centrifugation, we waited again, and the echogram built up so that the centrifugation hadn't destroyed the echo sources in this citrated blood sample. So the second point is that interfaces between groups of different cell types are also echo sources in tissues. Another experiment number 3, we are going back to the various samples of normal saturated blood with different cell counts, and we remember that the reflectivity increases with the cell count to a certain point, then decreases again. Why is that? Here at 10,000 cells per cubic millimeter we have mostly plasma, hardly any cells, so the interfaces are limited. Then as we increase the cell count, there are more cells, more interfaces between plasma and cells, and so the reflectivity increases. Then as we increase the cell density further, there's less plasma available, so the interfaces between plasma and cells decrease in number. Therefore, we know that the echo intensity from tissues, the reflectivity of tissues, depends on the number of small interfaces that are present. In the fourth experiment, we recorded the echograms from normal saturated blood, 3.6 million cells per cubic millimeter, that's the tissue model, and obtained this echogram. When we then stirred the blood with the glass rod, suddenly the spike had dropped quite a bit, and when we then waited, after 1 minute the spike height rose again slightly, after 3 minutes more, and after 5 minutes we had the original reflectivity of the blood sample, and that stayed then the same. In order to explain this phenomenon, we obtained frozen sections from the normal saturated blood with a cell count of 3.6 million cells per cubic millimeter. This frozen section was obtained immediately after stirring the blood sample. Given the blood sample 5 minutes of rest, the frozen section looks different. It should be emphasized that these were identical magnifications of both frozen sections, and they correspond to the echograms obtained after stirring, sudden decrease in spike height after rest period, return of the high spike height from before. What has happened here? We have a change in the size of the individual interfaces. They got much larger because of pseudo-agglutination. The same observation can be made by looking at citrated blood between two glass plates with the microscope. After knocking on the glass plates, the erythrocytes are separated from each other, giving them time. 5 minutes later they will form these large chains. Again, it should be emphasized that these were identical magnifications. It is the pseudo-agglutination that forms much larger acoustic interfaces than before. So we come to the conclusion: the size of small interfaces plays a major role for the echo-intensity, the so-called reflectivity of tissues. Abnormal ocular tissues differ also in their sound absorption. And when looking again at our series of citrated blood samples with different cell counts, we notice that there is a sound absorption that increases with the cell count. That's why the spike height declines so rapidly here. That's an angle kappa. And when we look at the 500,000 cells per cubic millimeter versus the 9 million cells per cubic millimeter, we see a clear-cut difference in the decline of spike height, the absorption sign, even though the spike height, the average spike height, is the same. So erythrocytes absorb much more than plasma. On the basis of these experiments, we can look at some clinical examples and apply our results. In the differentiation of tumors of the posterior eye segment, we have here again a malignant choroidal melanoma at tissue sensitivity, low spikes. Important should be mentioned here is to be perpendicular on the surface on either side, which are large interfaces. And here we have a hemangioma of the choroid. Quite a high reflectivity. And the explanation histologically is the small interfaces of the malignant melanoma versus the much larger interfaces, the septa of the structures of this hemangioma. When we apply this to the differentiation of orbital tumors, a metastatic carcinoma in the soft tissues of the orbit has a high reflectivity. It's lower in the center, where the infiltration is more intense and the cells are denser. This infiltration gives us a V shape, and we call this a high V. That's a tissue sensitivity. When we look at a malignant lymphoma, on the other hand, we get a low V. Malignant lymphoma is also infiltrative. The lowest reflectivity is in the center of the tumor, whereas towards the periphery, the high reflectivity of the normal tissues still influences the spike height. And when we look at the histology, we get the explanation. There's a larger interfaces in the metastatic carcinoma, much larger than in the lymphoma. So the size of the small interfaces is decisive. And the same thing is true for the anterior eye segment. We have here a benign nevus of the iris, high reflectivity, versus a malignant melanoma of the iris, low reflectivity. Again, the histology explains the cells are more in clumps in the nevus, but denser arranged with smaller interfaces in the melanoma. Now, turning to the differentiation of extraocular muscle diseases. Endocrine orbitopathy, the muscles have a high reflectivity. In myositis, the reflectivity of a muscle is low. The septal signals are much clearer, separated from the low spikes of the muscle interior. And when we look at the histology, we have the explanation again. These are larger interfaces than here in the myositis, where we have edema and cellular infiltration. So the echo intensity does depend on the size of small interfaces. And therefore we can use standardized A-scan at tissue sensitivity for tissue diagnosis.